So the case of liquids is actually very clear. But when it comes to solids, we saw that the situation is actually liquids, it's simple. Here we are saying that compare water and oil regarding flotation, and we see that oil floats on water. Similarly, water and salt water, water floats on top of salt water. We can show it, but right now, I mean, we'll not do it actually. It's a very nice experiment, actually, beautiful experiment. I can at least tell you, and you can try doing it at home. For that, what you'll need to do is prepare salt water and take some fresh water and take a slice of potato. So firstly, fill your bottle or glass with salt water and put a slice of potato, and it floats on top of salt water. Now, if you very slowly trickle ordinary water from the side of the glass so that it doesn't readily easily mix with the salt water below, the slice of potato remains in the center, and the top of the glass gets filled with ordinary. So in this beaker, we put salt water underneath, and actually on the salt water we put a potato slice, and we are slowly pouring water, plain water, and actually Hitesh is pouring it with the help of a dropper. One has to do it very gently, otherwise the two waters mix. If you don't allow them to mix, I mean, he's putting water on the walls of the beaker so that the water is slowly filling up, because this water is less dense. It's actually collecting on top, and so we know that a potato slice sinks in plain water but floats on salt water, so it's floating in the center. So now it's very clearly visible. I hope you can see that's floating in the center. If we pour more water, you can see it at half length or half depth. So it seems Benny Joseph sir is going. I don't know which all people are going, but thanks for coming to our session. Hope to see you next time. So friends, can you see the potato slice floating in the center? There is denser water below and less dense water on top. So denser water is the salt water, and on the top is plain water, and in between a potato slice is actually floating. So
if we add some color to the salt water or normal water, I think it will be easier to see the intersection.
Yeah, we can do that. See, maybe colored water, Hitesh can try. We have colored water. So it may get mixed up. I don't know. Like, we'll have to try that also. But right now, let's see the apple thing. So apple also is ready with its hole. So apple with the hole. So apple was floating when it was full without the hole. Isn't it spotlighted? It is spotlighted, Deepak. So, okay, now Hitesh, put it inside. What do you think will happen? This was floating earlier. Now will it float or sink? So Deepak is saying it will sink. Pavan Goda also says sink. Milan says sink. VG Vashish said it may float. So many people think it will sink. Let's see. Put it inside. It floats. So friends, so like I said, see when it's a question of liquids, the mystery is solved. Just the two densities of the two liquids decides the issue, and there's no complication. But when we come to solids, the matter isn't simple, and it's actually quite puzzling. So okay, here we have talked about now let's talk about solids. So we know that steel has a greater density than water, and steel's density is roughly 7 grams per cc. I mean, it depends on the quality of steel, what steel has many things mixed into it. So what exactly is there in the steel, it will depend on that. So relative density of steel would be 7. So what do you expect that we saw that any liquids with relative density greater than 1 will sink. But how about solids? Solids with relative density greater than 1, what happens to them? What do you expect? Varshita is saying you are not clear with potato slice floating. Don't worry, we'll explain it again. Vedant Sakre is saying if relative density is greater than 1, it will sink. So firstly, let me come back to the potato slice. Let me explain with the help of a simple diagram that I'm making on my...
Maybe we can show that what will happen to potato slice if you just put it in water, plain water. Maybe people have not seen it, so...
So here's so Hitesh is showing, wait, I will stop sharing. So Hitesh is taking a plain potato slice. Is it a slice? You'll have to cut it. Try cutting a thin slice. Right.
Tap water.
So tap water is there in the bigger bucket. So in water, plain water, potato slice sinks. So, but here you see on what is happening is we have Hitesh, can you make the camera focus on
this beaker visible?
So you see, in the small beaker, we have salt water below, and above that plain water. So actually plain water is floating on top of salt water. So this potato slice sank in the plain water, but stopped at the place where plain water ended and salt water began. So it's like the potato slice is showing the boundary of the two waters. It is sinking in plain water, but floating on salt water. Do you see that? Can you see, friends? I mean, this potato slice thing, is it understood? Varshita? Okay, yeah, Varshita now says she's understood. Okay, great. This experiment is otherwise easy, but only difficult to do because the two waters mix easily. So that's why Hitesh was putting with the help of a dropper. So that is the only difficult part. Now it has become straight. It's got disturbed and the waters have mixed probably. No, Hitesh is still trying to make it float because denser water will settle down, but yeah, they have mixed together, looks like. Anyway, so okay. Now we will come to the, like I said, when it comes to liquid, it's very clear. Relative density greater than 1 means the liquid will sink. Relative density less than 1, the liquid will float above water. Very clear. When it comes to solid, the situation becomes very strange. So, we'll come to solids. Firstly, let's begin with steel, which has very high relative density, 7. So any object of steel should sink because it has relative density 7. So let's start with a steel spoon. Wait, I'll have to stop sharing. So steel spoon sinks very clearly because it is so much denser. So relative density is 7. How about needle? Will it sink? Sink. Okay, put the needle. Sinks. But now let's take a steel cup, bowl, steel bowl. This also has relative density of 7. But when we put it in water, what do we see? It doesn't sink. It floats. So Vedant Sakre is saying bowl has air in it, so density reduced. You are right, Vedant, but that's something we will discover in other ways. So how does the shape, the bowl shape or other shapes change the density or relative density? That is what we are trying to explore now. So I will request Hitesh to, yeah, Shampa Majumdar is saying volume is more. Yes, Shampa, you people are right, but we are trying to show it through other experiments. So I will request Hitesh to now show an experiment with where we have taken a plastic bag with chana in it, chana seeds, gram seeds inside, and the plastic bag only with chana doesn't sink easily, so we have put some coins also inside. We have put a few coins inside so that it's heavy enough to sink. So now we'll put it in water. And it has sunk below, right? So very clearly this object which we have put has a relative density greater than 1. It sank in water. Now the same object, we will open up a little and we'll allow some air to get inside. So now we allow some air to get inside. Only some air, not too much is not needed. This is too much, actually, some air. And now this new object, it's the same object, but we allow a little bit of air to get inside and look, it's floating so comfortably. So what has happened, in fact, you can reduce the air and still float. What has happened is, now can you explain this? So Vedant Sakre has already explained, he's saying bag will float because more volume and not more mass. When air gets introduced inside, volume has become more because air has a lot of volume, but it has very little mass, very, very little mass. So the mass hasn't increased much, but the volume has increased much. So the bag floats. So is this clear to everyone? Vedant has explained it, but is it now clear to everyone else? So if you have understood this, what has happened, this new object, it's a combined object. The combined object has air, it has some solid, and it has some shape and formation. So this combined object, this combined new object has a lesser relative density because of introduction of air. Earlier, its relative density was more, but now with a little air, now the relative density has become less than 1, so it has started floating. And this is something we will do, we will see again and again. We will now show a very, very interesting experiment. So request to Hitesh to show the mothball experiment. So that's like, it's called dancing balls. So we will first show it, and I'll show you a photo as well. So we have taken a glass in which we will pour some Sprite, fresh Sprite. So you can take Sprite or soda water, anything which is a carbonated drink, which is a cold drink, carbonated drink basically. So it has like heavy amount of carbon dioxide gas dissolved inside. The moment Hitesh is opening, it is gas is making that sound. हितेश थोड़ा सा कैमरा नीचे करना पड़ेगा. You can see that so much carbon dioxide, it's making loads of bubbles. Pour some more. Shift the camera a little below. हाँ, और Sprite हटा दो. हाँ. Now we will actually put some mothballs, naphthalene balls. Nandini is saying it makes her want to drink. Yeah, before you, we feel like drinking it. Okay, so now putting mothballs. Now see what happens to mothballs. What? Sinks and then rises. Or what medalobus? Let's watch these. Isn't it strange? Crazy, yes. Sank first and then rises. Now show it close to the camera. I mean, bring the camera close, or show it with the other camera. So actually, you can see these balls very closely here. Show it from top as well as side. Do you see what's happening to these balls? And there, one ball goes down, then comes up again. Look at them very closely. Yes, as Nandini is saying, there are bubbles forming on them and then they come up. So yeah, as Pawan Goda is also saying, that it's like the Vedant also saying CO2 bubbles get stuck to the balls and they reduce density and cause flotation. Yeah, the relative density of these objects become less. Earlier, the relative density was more because they sank. But now, because of the bubbles, their volume increased, relative density, overall density decreases, and so they float. Yeah, the balls are attracting bubbles. They have some quality. I mean, there must be some reason, some chemical reason why these balls attract bubbles towards themselves. So when bubbles burst, sometimes they come down. I mean, after floating for a little while, the bubbles burst and they come down also. So this is one interesting case where there's constantly going up and down, same as we saw in lava lamp. In lava lamp also we saw oil going down and up and going down and up. Yes, it's a very interesting experiment. Hitesh is now trying to push them down, but they refuse to go down. They will go down by themselves when their bubbles burst. Yeah, this one went down, new one. See, it doesn't rise immediately up. It first collects bubbles and then rises up. And there's now competition with space. Yes, this is a very interesting experiment. Great fun. Much more fun than drinking this Sprite.
Who wants to drink this Sprite?
Yeah, Hitesh is asking who wants to drink this Sprite now. Actually, Sprite is absolutely fresh. Yeah, this is a crazy experiment. And actually, the similar thing happens in that lava lamp also. That salt sticks around oil droplets. You remember, and they become heavy and go down. But then the salt dissolves in water, and then oil comes up. Then oil takes some salt, goes down. Then the salt dissolves and it comes up. So it's like the similar phenomena is happening here as well. Okay, friends. So I think, yeah, like Varshita is saying, oil goes down with the salt and back to its position in the earlier lava lamp experiment. So a similar thing happening here. Now, friends, let's come back to our discussion. So we have finally caught the culprit. Culprit means what makes things float and sink. It is basically, as we realize, that it is the relative density of the combined object. The combined object, if its relative density is more than water, it will sink. Less than water, it will float. So can you now explain the spoon and bowl? The steel spoon and bowl, can anybody explain?
People can unmute and speak if they want.
Yeah, you can unmute and speak. Vedant Sakre, one request, please give others a chance also. Whenever we ask a question, if one person answers all the questions, others don't get a chance. Manan Agarwal, we are not finished. Actually, we go up to Archimedes Principle and Principle of Buoyancy. Yeah, my question is, now can you explain why a steel bowl floats but a steel spoon sinks? I mean, we had raised this question, why a steel bowl, a bowl of steel actually floats, but a spoon sinks. So why does the shape matter here? So that is the question. So one or two people have tried answering it. Yeah, you can unmute and answer if you want. Yes, so the spoon doesn't have the space which will capture air. So it's how the combined object gets created. So if the combined object has weight and volume of air also added to it, so like Parth Verma has also said, a steel spoon has a density of 7, but in case of bowl, mass is same, but volume is increased, so the density is decreased. Yes, in a bowl, the volume becomes large because there's inside air fills up the bowl, and
Ma'am, can I?
Yes, please.
Ma'am, can I answer in Hindi?
Yes, please.
क्योंकि मैम जो बॉल है उसका जो ऊपर का हिस्सा है वो खाली है, जिसमें जब हम उसे फ्लोट कर वो पानी में डाल दें तो उसमें हवा भरी रह रही है, जिससे जो उसका वॉल्यूम है वो बढ़ जा रहा है, लेकिन मास से नहीं बढ़ पा रहा है, जिससे उसकी डेंसिटी वो घट जा रही है, जिस कारण वो फ्लोट कर रहा है.
Very nice, excellent. So many of you have given the answer correctly. That basically its density, overall density, combined density of this whole thing of bowl plus air is actually combined relative density is less than water. So it starts floating. So now friends, we saw the chana one also, and so we have reached this conclusion: the density of the combined object, of the new object, the thing floats because its density of the combined object is less than water because of air, which has very little mass but a lot of volume. So such things float. In fact, that's the reason humans also can float easily on water. And in fact, we will just show you a aluminum foil. So Hitesh, can you show aluminum foil? We will see that aluminum foil can, if we put it over water, Vikas, can you spotlight that video? Yeah, Shampa, volume of bowl is far more than the spoon. And we are now showing, Hitesh is showing the his container in which he will show aluminum foil in two ways. If we take just a piece of aluminum, right, and we put it flat on water, if we put it flat on water, it starts floating. Can you show from top? It floats. See, it's floating. Now, if the same thing we put standing in water vertically, if you put, then it sinks, because aluminum by itself has a greater density than water. But then when we put it flat, the air above also contributes to the combined object, whatever is formed, and therefore, yeah, Shampa is saying volume is more, buoyant force is more, but buoyant force is not a word we have used as yet. We haven't explained it. So we can simply say that the relative density of the combined object is less, so it floats. So now we'll go to the last part of today. We have shown you aluminum foil. We have shown you dancing balls, mothballs plus soda. Now we will get to the very famous Archimedes Principle, which I'm sure you will all have heard about, and not only heard, you have, wait, where is that? You've seen this picture, no? I mean, similar picture. You've heard about this story of Archimedes shouting, "Eureka, Eureka," and jumping out of a bathtub and running to the king's palace. Have you all heard about it? So we come to that famous Archimedes and his principle, and we will actually derive the principle right in front of us. And this is one of the few principles of science which can be derived so directly. I mean, there are very few actually principles which can be shown in front of your eyes. This is one of them. So what we are doing is, Hitesh, I will just stop sharing. So Hitesh is taking an overflow can So overflow can is actually used to keep the water at exactly the same level in a container, and any extra water from that level will start flowing out of the overflow pipe. So any extra water we can collect. To collect the extra water, this overflow can is used. We have just made it ourselves. You get it in the market also, but we made it with just a plastic pen refill, and pen tube and a plastic beaker. So what we have done is taken an overflow can, put another pan underneath. So there is a beaker we have kept underneath, and under the beaker we have kept a balance, a weighing balance, a digital weighing balance. Hitesh, if you move the camera just a bit lower, then it will be visible. So we are showing you the experimental setup. So you see the small beaker which will collect spill water has a small weighing balance under it, and above that there is this overflow can, right? And now Hitesh will take a stone which we have tied with a string. So the first thing we will do is take this weight of the stone in air, and all of you are required to note it down. So here's a stone which the weight we will read on the spring balance. We have hung the stone with a thread. So he will show with his other mobile, he will show the weight of the stone in air. So what is the weight of the stone in air? I mean, I can't see the reading. The reading will have to be brought in front, Ritesh, for us to see. It seems to be somewhere around 100. Yeah, so seems like 100 grams. So, okay, it is 100 grams, nearly 100 grams. It's not very accurate. Spring balance is not really often very accurate, but 100 grams is the weight of stone in air. Now, the next thing we are measuring is weight of stone in water. So we will hang the stone inside water, inside the overflow can. Yeah, so the mass is actually, instead of mass, we should take weight. Oh, Hitesh is saying the balance has gotten some problem because of water. Some water spilled over it. So should we get another balance?
बैटरीज को प्रेस करके देखो.
Vikas is saying press the battery a little. Otherwise, I'll get another balance. हाँ, नहीं वो नीचे किचन में रखा है. Wait, यहाँ वाला चल नहीं रहा.
नहीं, there is one more working.
अच्छा, there is one more working. Okay. So while Hitesh is getting the next balance, I'll explain. See, Archimedes discovered, we all discover, whenever we go inside water or inside any liquid, the first thing we feel as if the liquid is, as if our weight is reduced. The liquid is pushing us up. This we feel very clearly in water. Those of you who have gone for swimming in swimming pools or a river or a pond, you feel very light because it seems that the water is pushing you up. So any body, when it is put inside water, actually loses weight because the water pushes from below. Yeah, like Nandini says, it's very easy to lift a heavy person in water because the person has very little weight actually. So this was realized very clearly that the water pushes any body up and the body loses weight. but we don't know how much weight it loses. And the Archimedes principle tells us something very important about it. Kishore, if my voice is cracking, you will have to check your connection because it's probably not cracking for others. You'll have to check your device or the device settings or the internet connection. So Archimedes told us that the Archimedes principle tells us, take the weight of something in air, then take this weight of the same thing in water and find the difference, find the loss in weight. Also, collect the water which that thing displaces. When it actually gets into water, it shifts water, no? It displaces water. It displaces water according to its own volume. So it actually shifts water, displaces water. So collect that water. And you will then realize a very important connection between the two. So that's what we are going to be doing. So the first thing, we took weight in air, which was 100. Now we will take weight in water. And simultaneously, while we'll dip it in water, we will be collecting the spillover, the spilled water in the beaker below. So this is, here comes the weight in water. Dip the whole stone inside water, and the spill water is collecting, that's displaced water is collecting, and what we are getting is about 50, seems to be around 50, right? Yeah, it's nearly 50. So 50 grams is the loss in weight. So here the loss in weight is 50. Now let's see the weight of the water we have collected on the other side. So Hitesh is showing the screen of the other device. So this has come to 42.6, is it?
Is increasing. It is close to 43 right now.
It is close to 43, but did you adjust it for the, he adjusted for the weight of the beaker, but yeah, so currently we did not get a very exact value. We got 43 and 50.
The water is still dripping actually.
The water is still dripping. Hitesh, is it some of it above water surface, or all of it has gone?
Stone?
The stone.
Yeah, it is fully submerged.
Fully submerged, but still some water is. Hitesh is changing his position.
It is 55 or something.
Accurately
to see. Okay, I'll show it again.
So firstly, let's see that, and the stone shouldn't be touching from the sides of the vessel. Shouldn't be touching the sides of the vessel. So this is somewhere around, I mean, we can't see it accurately. Somewhere around 50.
55 it is almost.
He's saying it's probably 55. And now see the other one.
So it lost 45 grams almost, more or less.
So this is about
46.5.
46. Okay, so friends, our calculation are going to be like this. I'm showing you the screen. The weight of stone in air is 55.
What it lost is 45.
Weight of stone in water is 55. No, sorry. Weight of stone in air was 100. Weight of stone in water is 55. Right? So the difference is 45, right? Okay. Are you writing, friends? So weight of stone in air is 100. Right now, everything is in grams. It should be in newtons, but right now everything is in grams. So weight of stone in air is 100. Weight of stone in water is 55. And so what we get is loss of weight in water, which comes out to be 45 grams, which is weight in air minus weight in water. So we get 45 grams. And on the other screen, what we read is, what was the reading? 46 point, let me stop sharing.
47.6.
It is 47.6. What Hitesh is reading is 47.6. So actually, that's what we are seeing. Look at the statement which is there on the screen right now. Loss of weight in, huh?
Presentation clear.
Oh, sorry,
We cannot
friends.
see the screen.
Sorry, friends. Can you see now? So, okay, let me show that. Firstly, we saw the weight of stone in air, which was 100, weight of stone in water, which was 55. And then we calculated loss of weight in water, which was weight in air minus weight in water, which came out to be 45. Now, this is near about, not very exact, but then we come to the Archimedes principle, which tells you that loss of weight in water is equal to the weight of liquid displaced. In our case, we got one side, we got 45. The loss of weight in water we got as 45, and weight of liquid displaced we got as 46.5. So there is a little error, which we will get because our equipment is not very accurate. But this is what the Archimedes principle tells you. This is the famous Archimedes principle, which says that a body will lose as much weight as it will, as the weight of the water it will displace. It will lose an equal amount of weight. So this has very important implications, which we will come to now. Parth Verma is saying the thread is the reason for the error. Yes, we'll have some reasons for error, of course. So yeah, thread will make a difference also. But yeah, we see it near about. Okay, now we will see that this tells us many things. Firstly, okay, so here you see the picture of Archimedes jumping up and running about, because he discovered that how with using this principle he could detect fraud when a crown for his king was to be made in gold, and there was some like some other metals mixed up. There was some cheating, so he could discover cheating through this. But first, let's see. Firstly, why is there is loss in weight? Look at the screen. Can you all see the screen? So, so do you see that any body? First, look at the left-hand side. Any body which is inside water experiences two kinds of forces. One is its own weight, which is mg. So its weight acts downward, which is the Earth's pull on it. So the body will always have constant weight. The value of mg will always be the same, right? But it experiences a force upwards, which is the force which water gives upwards, which we call it upthrust. The thrust which the water gives upwards, it is called upthrust or buoyant force. So it is a support force. The water supports with this force, or water pushes up with this force. So these two forces have to balance each other. I mean, they contradict each other. So in the case A, when the body sinks right below, weight is more than U. U is upthrust. Weight is more than U, so the body sinks down because it is pulled down by more force and pulled up by lesser force, so it sinks below. When the body floats in somewhere in middle or below the surface of water, U and mg are exactly the same. Both forces are actually balancing each other, so body is quietly floating because it is being pulled down by the same force and it is being pushed up by the same force. So both the forces balance each other, the upthrust and weight, and the body floats like that. But when a body floats above water, part of the body is above water, you see, this is the interesting case. Weight is the same, mg is the same, but now the weight of liquid displaced has become less. Less liquid is displaced. Now less amount of volume is dipped in water. So less liquid is displaced. And so the upthrust will be a weight of this water, which I'm showing with the red dot. It will be weight of this this water, and not the upper volume will not matter. Only the weight of the liquid displaced will matter. So upthrust has actually become less. So this is now directly balancing the weight. I mean, if this whole body was going down, if the if we push this body down, the upthrust will become more than the weight, and the body will jump up. It will be thrown up because upthrust will become greater. This is something we see very clearly in the case of a thermocol ball or wood. So I would request first Hitesh to show, push a thermocol ball and show how it jumps up. And then we will weigh a wooden block in water. We'll weigh a wooden block outside and we'll weigh it inside water. So first he's showing how, look at this thermocol ball. It's mostly floating on above water. There's very little of it is actually dipped inside water, and that will be the upthrust. Upthrust will be the weight of that much liquid. And if we push it down, upthrust increases and the body is thrown up. The upthrust becomes more, so body is actually pushed up. Kishore Kumar, yes, we'll share the slides with you on the WhatsApp group. And now we will weigh the wooden block first in air, then in water. Is upthrust same for a given liquid? Vedant, upthrust depends on the weight of liquid displaced. So remember, whatever is the liquid displaced, accordingly there will be upthrust. So okay, right now, can you see it? Wait. So right now Hitesh has hung a wooden block, and the weight is it is somewhere around. Hitesh, you will have to read. It is above 50.
Somewhere around 75.
Somewhere between 65 to 70. Yeah.
So somewhere between 65 to 70, right? That's its weight. So suppose 65 grams, or let's say 67 grams. Now bring it to water, dip it in water. So we will dip it in water. And we know that it floats with some part above water and some part below water. You see, in this condition, when it's freely floating, the upthrust and weight are exactly cancelling each other. So if you try reading on the scale, the reading comes as 0. 0 because weight is not pulling it down at all. Weight is being exactly balanced by the upthrust. And the wood has settled in a place where it can, I mean, only that much portion is dipped below, which can cancel its weight. So both are cancelling each other, and the body is weightless. It becomes actually weightless. When you are floating on water, you are weightless. हाँ दिख रहा है आराम से, one can see it clearly, right? Okay, so coming to the next slide. So this is what I mean, the slide is showing you that can you see my screen? So as the slide is showing, when a body is floating half submerged or some part submerged in water, here actually it will come to this state only when buoyant force is more than weight. I mean, if the whole body was inside, the buoyant force will become more, and it will push the body up so that it floats and both become equal. So when buoyant force becomes more, the body floats like that. In a sinking situation, weight is more. When it sinks, the buoyant force is less and weight is more, so the body sinks. Right? Okay, have you understood till here? Have you understood till here? Is there any question or doubt? Harshit is saying he has a doubt. Please ask. Parth is asking, what if the weight and buoyant force are equal? So, like I just showed, I'll go back to the screen. Just a sec. I will just first, Parth, look at the case C here. In case C, and even in case B, wherever the body floats freely, actually the upthrust and weight are equal. So firstly, in case B, they are exactly equal. They are cancelling each other. So body is floating freely. In this case C, if the body was fully immersed, if you tried to pushing the body inside water, the upthrust will become more because more water was displaced. So the body will be thrown up. The upthrust is more, so body is thrown up and it settles in a place where the upthrust and weight become equal. I mean, some part of the body remains submerged. You remember the upthrust is equal to the weight of water displaced. The upper force is equal to the weight of the water displaced. So here, the body is not fully displacing, I mean, the whole of the body is not displacing water, only some part of it, the lower part of it is displacing water. So upthrust will settle in a place where upthrust and weight become exactly equal. So here, when it's freely floating, anything which is freely floating, upthrust and weight become equal, and the body shows no weight. It doesn't go down. And if you try reading the weight on a scale, it will come 0, as we just saw on the spring balance. Now, why a live person gets sink and a dead body float? Harshit, actually dead bodies often get filled up with gases. There's decomposition starts inside the body, and the lungs and other parts of the body actually fill up with gas, and that makes it float. And a live person sinks because you saw the aluminum foil. The aluminum foil, when we had put it straight, it sank because overall our body weight is slightly more than water. But we can make our body float by lying flat on water surface, or if we fill up our lungs with some more air, then we can make ourselves float. Or when we wear air-filled jackets. Have you seen how people wear life jackets which are air-filled? When we wear life jackets, then we are increasing our overall, so we are decreasing our overall density. We are decreasing our relative density. So Vedant is asking, how does buoyant force relate with density? So Vedant, if you see the diagram, look at the screen. See, the upthrust is equal to the weight of the liquid displaced. So upthrust will depend on the density of the liquid, whereas the weight of the body will depend on the density of the body. So it is two densities actually balancing against each other. One is the density of the body, and one is the density of the water, liquid, right? So basically here also it's a case of relative density only. relative density of the body in comparison with water. Is there any more question? There are one or two examples. Yes, Parth, we are showing examples. If you wait just a little, we will show examples. We made an experiment to show that a metal ball float because of air, but if we made it as vacuum, does the bowl sink or float? Okay, so friends, we are showing you two situations. One situation, the metal bowl, we keep it, look at Hitesh's screen. The metal bowl will float only if we keep it horizontally. I mean, we keep it flat like that. If we keep it like this, then it will float. But if we tilt it, I think you will have to take the other camera. If we tilt and put it inside, it can actually sink. Because now it is sinking only because of its own weight and no air. No air, I mean, because he tilted it, some water filled up and the air went out. There's no place for air. So now, because steel is so much more dense, so it basically sank. So one is this. The second is a very beautiful example we will show you with the help of a plastic beaker or a plastic mug. So Hitesh will take a plastic beaker. Let's see if it's visible with the beaker. Otherwise, we'll take the colored mug. So here's the plastic beaker. See, this beaker, first let me explain, Hitesh. This beaker will displace water as much as its own volume, right? When we fill it with water, its weight will be same as the weight it displaces. When we fill it with water, notice my sentence. When we fill it up with water, Hitesh, outside. Right now, its weight, Hitesh.
The other camera,
Vikas. Vikas, spotlight the other camera. So now when we have filled it up with water, its weight will be same as the weight as the liquid it displaces. It will displace the same amount of liquid. I mean, it will displace its own weight of its own volume, according to its own volume. So its own weight and the weight of the liquid displaced are same. So see how it floats. This is situation B. Just let it come on top. Just keep it straight. It floats right on top of water, just touching the surface of water, because its own weight is same as the weight of liquid it's displacing. Think about it. It's a very beautiful example of Archimedes principle. Is this clear?
Because the other camera.
So is there any question? I mean, our time is actually over, but we have just one or two activities more left to show. So we'll just finish with them. But okay, Daksh is saying, I should say that again. Okay, Hitesh, can you take this out? Suppose this has, I mean, right now, suppose it has, let's say, 50 milliliters of water, or its weight is, okay, 250 milliliters of water. So its weight is 250 grams. Suppose this is the 250 gram, it has weight. So because the plastic has very little weight, the total weight is basically because of water inside, right? All its weight is coming from water inside. Now, if I dip it in water, Hitesh, do it slowly. Now, when we dip it in water, it is displacing water as much as this volume. The same 250 milliliters it's displacing, and the weight of that liquid displaced will also be 250 grams. So the weight of this beaker filled with water and the weight of liquid displaced are exactly the same because the plastic is very thin, it has very little weight. So because the two things are same, it is floating right at the surface of the water, right inside water, almost at the surface. Sachudan is saying metal ball floats because of air, but we make it as vacuum. Does the ball sink or float? See, in the second case, when we tilted it, air has gone. Air has gone. If you treat it only as steel, rest of it is water inside the container. So if it's only steel, it sinks. When it is steel plus air, it floats. But when it's only steel, it sinks. Any steel which is only steel sinks. Vikas is saying you won't be able to create vacuum. Yeah, it won't be a simple exercise, but you can remove air, no? I mean, you don't need to create a vacuum, you can remove air. What we did was by tilting, we removed air, that's all. Okay, so now we are left with just... Acha, Hitesh is filling the beaker half.
Can you see this?
Because
highlights. Because could you please spotlight?
So when we fill it half, see where it floats. I think it will tilt, but anyway, try. It tilts actually, but it floats half above, half below.
You can try this paper cup.
Try the paper cup. Yeah, but I mean, it's difficult to keep them straight.
You can try
But I want to finish with that Archimedes story because many people are going now. So now there's just very little left for us to do. I'm screen sharing. Can you see my screen? So we showed you with a wooden block. Now you see, if you see this image, see if something is floating freely in water, weight and upthrust are equal, like we told you. Think of a wooden block, partially submerged. So, and its overall weight is less. The upthrust is as much as the weight, which is as the amount, the weight of the liquid it is displacing, which is the below portion. That much is the upthrust. So it's floating like this. If we add more weight to it, suppose we make an elephant stand on it, the weight increases, the block sinks so that more of it actually is submerged. Upthrust increases to adjust that weight, to match that weight. Upthrust will have to increase. It increases because the block sinks further down to adjust. Still weight and upthrust are same, but the block is now submerged more. So that's the important thing to understand, for which we will tell you a story of a boatman and passengers. So I think, yeah, this is the last story we are telling you. So I will stop sharing and Hitesh will show it on the, so with the paper cup. No, but it happens better with paper cup. We haven't tried with this one. Okay, Hitesh is trying. We were doing it with paper cup. Hitesh says we'll try with steel bowl. So we have a boat in which a boatman is saying, "Come, passengers, come. I'm starting for a journey from one village to another. We have to go. Come." So one passenger comes. "Come, more space. Please sit. come, 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 another passenger, another passenger, another passenger, another passenger. Wait, don't fill up, don't fill up. The boatman is saying, please don't come, my boat cannot take so many people. But people don't listen. They keep coming and the boat keeps sinking down to adjust the weight. And the boatman is saying, please don't come, no more people, no more people, please. But people are not listening. I want to go, I want to go, I want to go, I want to go. Until what happens, too many people fill inside the boat and the boat goes, it hasn't gone, boat goes down, boat sinks. Because it sinks more and more to increase the upthrust. The weight becomes more, so upthrust has to be increased. How can it be increased? By displacing more water. So it goes down to displace more water and more water and more water till the weight becomes too much. It cannot displace any more water and it sinks. Right? The same idea has been shown here using the example of a ship. So here they have shown a ship which has 500 Newton weight is there. Weight is 500 Newtons. So upthrust, ship is floating comfortably. So upthrust is also 500 Newtons. So people put more weight on the ship. Weight becomes 750 Newtons. So a ship sinks a little more and upthrust increases and becomes 750 Newtons. People are still not satisfied. They put more weight. They put 1000 Newtons weight. So the ship sinks a little more, but this is the maximum upthrust. You see the ship is sunk to its capacity, is displacing water to its capacity. The full volume of the ship has come down. This is the maximum upthrust of 1000 Newtons. Both are still balancing, but a little more weight becomes 1250 Newtons. But the upthrust, the maximum upthrust could only be 1000 Newtons, so the ship sinks. So that is the thing we were trying to show through the boat story as well. So friends, if you have any question, you can ask. We are through with our experiments and demonstrations. Pawan Goda is asking for webinar on astronomy. Whenever we offer it next, if you are there on our WhatsApp group where we announce our sessions, you will get to know about it. We keep repeating sessions also. Half full beaker we showed. Vedant is asking, in case 3, the upper layer of weight should coincide with the upper layer of water. Vedant, what they are trying to show is that ship is the one which is carrying loads. So ship, maximum it can sink up to its edge. A boat also can maximum sink up to its edge, as we were showing with the help of a bowl also. If you put more weight, water will start coming in. So Parth Verma is asking, you mean to say that the weight of the object on the ship should be less than the ship's weight itself? I'm not saying that. I'm saying the ship's volume should be so that, see, it will displace water according to its volume. A ship with a larger volume will displace more water, and so it can carry a larger weight. It will receive greater upthrust. So it's decided by the ship's volume. So a larger boat can carry more weight, a smaller boat can carry less weight. Varshita, thank you so much. Parth Verma, I did not make this statement. I am saying a ship will displace water according to its volume. You have to,
ma'am.
Yeah.
मैम जब जो अप थ्रस्ट है वो 75 N है और वेट 75 N है, तो जो शिप है वो 500 N, जब उसकी पावर टाइप जब लगी थी 500 N और अप थ्रस्ट और वेट 500 N था, वैसी क्यों नहीं रही?
देखो, मैं फिर से वो दिखा रही हूँ, मैं फिर से वो स्लाइड दिखाती हूँ। सी इस स्लाइड को फिर से देखो, अभी शिप जो है पानी के काफी, शिप का बहुत सारा हिस्सा पानी के ऊपर है। नोटिस कि शिप का खुद का हिस्सा कितना डूबा हुआ है, शिप का खाली नीचे का हिस्सा डूबा हुआ है। और इस केस में जो शिप का खुद का वेट और उसमें सामान रखा था उस सबका वेट 500 न्यूटन था। तो ये जितना डूबा हुआ था वो इतना ही डूबा शिप, और उसका वो इतने डूबे हुए हिस्से का इस समय की वजह से जो अपथ्रस्ट मिल रहा था, ध्यान है ना, अपथ्रस्ट होता है कितना, इस डूबे के हिस्से हुए के, इस डूबे हुए हिस्से का पानी जो है उसका वजन जितना होता है। तो इतने पानी का वजन 500 हो गया और उतना ही अपथ्रस्ट हो गया, तो ये शिप आराम से तैर रहा है। ठीक है, पहली केस में आराम से तैर रहा है। दूसरे केस में शिप पे थोड़ा वजन और लादा गया। ठीक है, और वजन लादा गया तो टोटल वेट शिप का खुद का और सामान का वेट हो गया 750 न्यूटन्स। ठीक है, तो शिप थोड़ा और डूब गया। देखो पिछली बार से ज्यादा डूब गया, ताकि डूबा हुआ हिस्सा बढ़ गया, तो डूबा हुआ हिस्सा वो इतना और डूबा ताकि डूबे हुए हिस्से का वजन 750 हो सके। अब डूबे हुए हिस्से का मतलब डूबे हुए हिस्से का जो पानी है, मतलब वेट ऑफ वाटर डिस्प्लेस्ड, शिप का खुद का नहीं, वेट ऑफ वाटर डिस्प्लेस्ड, ये जो जितना हिस्सा डूबा हुआ है इतना पानी जो है उसका वजन 750 है, तो अपथ्रस्ट 750 हो गया। तो अभी भी इतना सारा वजन संभल गया, जितना वजन हमने इस पे लादा था उतना ही अपथ्रस्ट हो गया, संभल गया। अब इन्होंने जिसने भी इसने शिप पे और सामान लाद दिया, शिप बिल्कुल अपने एज तक डूब गया है, अपने सिरे तक डूब गया है, और टोटल डूबा हुआ जो शिप है, इस इतना यहाँ पे जितना पानी है उस पानी का वजन अब 1000 है। तो वेट भी 1000 है और शिप भी, ये अपथ्रस्ट भी 1000 है। तो ये दोनों एक दूसरे को जस्ट बैलेंस कर रहे हैं और शिप अभी तक बचा हुआ है। बस अब इसके बाद जरा भी अगर हम वजन और ला देंगे, जो कि इन्होंने किया, इन्होंने इस पे 250 न्यूटन और वजन लाद दिया, तो देखो शिप के एज के, मतलब अब शिप को जो है इतने वजन को संभालने के लिए और डूबना पड़ेगा, लेकिन अब और डूबा तो इसके एज से तो पानी अंदर और भरने लग गया, शिप के अंदर पानी चला गया। वो अपने, जैसे हमारी कटोरी में हुआ था ना, कटोरी अपने सिरे तक ही तो पानी को बचा सकती है, बाद में तो पानी अंदर भरना चालू हो जाएगा। तो ये शिप के अंदर पानी भर जाएगा, तो अब तो शिप डूब ही जाएगा। तो मतलब ज्यादा से ज्यादा इन्होंने ये दिखाया है कि शिप का टोटल वॉल्यूम जितना है, वो टोटल वॉल्यूम के बराबर वो पानी में अंदर जा सकता है, जैसा कि हमारी नाव में भी हुआ था। और अपथ्रस्ट जो है ज्यादा से ज्यादा उतना हो सकता है, उतने ज्यादा पानी का, उतने सारे पानी का, उतने पानी के उतने वॉल्यूम का जितना वजन है। तो इस केस में इन्होंने 1000 दिखाया कि 1000 जो है ज्यादा से ज्यादा इतने पानी का वजन है, उतना ही ये शिप संभाल सकता है, उतना ही वजन, खुद का वजन और उस पर लादे हुए सामान का वजन 1000 से ऊपर नहीं होना चाहिए। 1000 से ऊपर आपने किया और पानी, मतलब शिप को और नीचे बैठना पड़ेगा, और नीचे बैठेगा तो इसके अंदर पानी भर जाएगा।